हेलो फ्रेंड्स, होप यू डूइंग वेल। सब कुछ बढ़िया और लाइफ सही चल रही है। ठीक है, पढ़ लेते थोड़ा सा। तो हमने लास्ट क्लास में थोड़ी सी मोटिवेशनल बातें की थी और we talked about how we can clear gate and stuff like that, and I tried to be a real good guru, but today we'll be talking about important things, and this is where we start our original sense of preparation, and we'll do a chapter wise analysis. Like I told you in the very first video, I'll be going in a very in a structured way, not in a random way, right? So if you're talking about let's say if you're talking about a reservoir rock, if you're talking about reservoir engineering in total, how would you go about it? लाइक बच्चे को पूछेंगे रिजर्वर इंजीनियरिंग क्या सीन है, तो वो बोलेगा कि एक कंटेनर है, उसमें फ्लूइड है और उसके थ्रू हम वेल्स ड्रिल करते हैं और प्रोड्यूस करते हैं। बिल्कुल सही बात है। तो क्यों ना हम पढ़े भी उस तरीके से? व्हाई नॉट स्टडी इन अ वे इन विच वी थिंक इन आवर माइंड्स? इफ यू आर नॉट पेट्रोलियम इंजीनियर्स एंड इफ यू आर समवन फ्रॉम द अदर डोमेन, we'd still have to recollect and connect with those guys just so that we test our understanding. That's how I will try to go, and we'll be going about things in this way. We'll be first talking about the stencil, which is the rock or the skeleton, जहाँ पे सब कुछ stored है, the container itself. The second thing we'll be talking about is the fluid which is stored inside it, and the third thing we'll be talking about the recovery options and the various analysis about the drive energies and recovery efficiencies and stuff like that, right? So that's how I'll be going about things, and let's write the first chapter name that we'll be discussing today. Chapter 1 we'll be talking about the rock properties. As always, we'll be talking from the very scratch, zero level. If you've never understood or never read about things, people have contacted me saying that they have zero knowledge in reservoir engineering. Trust me, it does not require a lot of basic knowledge or predetermined knowledge और पहले से आप कुछ rocket science दिमाग में रखने की जरूरत नहीं. It's very easy to understand, don't worry. And while we go about it, we'll be talking about. I've brought my notes today so that I don't lose out on anything that I can share with you, and I'll share these notes as well with you, right? So rock properties. Why are we talking about this in the first chapter? Because if you're talking about a reservoir, let's say this is your reservoir, and this is the rock which I'm shading in black. Black is my favorite color. So this is a reservoir rock, right? I'm trying to draw it like a container. So if we study about this container first, we can study about its fluids then, right? Otherwise, if you start about the fluids without having idea about where the fluids are, it does not make sense, right? So in the reservoir, fluids are stored. The fluids can have various forms of distributions, right? The fluids, there can be various phenomena, various kinds of parameters guiding the storage of this fluid inside the reservoir, and that is another study that we'll be covering, right? So this is the rock, this is the fluid, and then the various way in which we can produce fluids production. Right? So today our focus is on the black part, the shaded black storage or the container, and we'll be talking about things like porosity in detail. How can we measure porosity? We'll try to solve a few numericals as well, and I'll try to convey how these numbers come into existence and how do you measure the average porosity, how to consider the variation in porosity and all. So hang on with me a bit, okay? I need to get my duster. Right. So yeah. So let me draw a diagram about a rock. Okay. So this is a rock, and these are the pores, right? And here fluid is stored. Another example can be you have a room like this room, right? And you can imagine a cube-shaped room, right? And then there are balls placed at the edges of the cube, like this, right? I hope you can imagine, right? And the spaces that you can see in between, these are what? These are pores, right? So these are the solid boulder type rocks that are, we call them as grains, the rock grains, right? And the fluid is stored in whatever space the grains leave in between. So this is known as, this constitutes porosity. It's not known as porosity. So that is what I'm trying to convey. So this space, right? So porosity, what is porosity? Porosity is this red space, whatever this red space is, divided by the bulk volume. Okay. A lot of people get confused between the pore volume and porosity. A lot of people say this is the porosity. It's not the porosity. Porosity is this divided by the bulk volume. And what's the bulk volume? It's the geometrical bulk volume, right? And this is very important. It's not a simple thing, and it's not casually, you cannot take it casual, because if you understand this definition, I'll try to explain you a very important thing. For example, you have 3 cubes of different sizes. One cube is 1 centimeter. Okay. The second cube is, let's say, okay, let's put it this way. For example, you have 3 cases. First case is you have distributed, or you have a room full of, or a cube full of tennis balls, right? The second example is that you have a room full of table tennis balls, right? And the third example is you have a cube or anything full of basketballs, right? And every room or every cube is distributed with balls like this. Will they have, let me ask you a question. Which one of these cases will have the largest porosity? If you want me to draw a diagram, I will do it for you. For example, this is what I'm talking about. Just looking at it from the front, okay? So this is case 1. Okay, this is case 2. And this is case 3. It's a cube, it's not a square, it's a cube. It carries on each area. So this is case A, this is case B, and this is case C. This is a tennis ball, this is a table tennis ball, this is a tennis ball, and this is a basketball. And assume that these are not hollow from inside. Just for the size, I'm giving these names. So I'll ask you, which of these guys has the largest porosity? Any guesses? Okay, so I'll tell you the answer. You can pause and just think about it, but I'll tell you the answer. The highest porosity is endowment. Each of them have the same porosity. And that's why this definition is very important. Porosity is pore volume upon bulk volume. This bulk volume, this ratio thing, pore volume upon bulk volume, is what is causing the beautiful scenario over here. What's varying over here is the bulk volume, okay? But what's also varying is the pore volume, and both are varying in, say, proportion to each other. The packing phenomena is same. Now, if I say that, if I fix a ball in between and these I leave untouched, now I can say that there is some mismatch in the porosity. There can be an arrangement. So this rock, now it comes to another concept. So this is called the grains, rock grain, or the clast. And this is called the matrix, or the not matrix, we call it cement. Cement is something which is smaller than a grain, and it fixes the spaces between the rock grains, right? So this is a bit of intuition about what porosity is, and I'll tell you other examples related to that. But now let's get into formal study kind of thing, like we do in schools. I'll give you definitions, and it's important that is also important, because you need to have a language base as well. Someone asks you about porosity, you cannot draw these diagrams all the time. You have to have a language set as well. So that is what I'm trying to tell you right now. Let's write some definitions. Okay. So there are 2 kinds of porosity. One is basically there are a lot of kinds, but what I'm trying to convey over here is total porosity, effective porosity, and hydrocarbon porosity. These two guys are important for our petroleum recovery systems. This is theoretical, okay? And the way we measure the porosity gives different porosities. And I'll tell you how we measure the porosity. Okay, effective porosity is, if I tell you, this is my rock. I've shown this example before. So this is my rock. Okay, so these guys are the pores. So now, if I name these pores, okay, this is my pore A, B, C, D, E, F, G, and this guy, this whole ball has the bulk volume of BV. Okay, so if I quantify the total porosity, the total porosity will be phi total will be A plus B plus so on up to every pore, the volume contained by every pore divided by the bulk volume. Okay, but the effective porosity, guys, over here is F plus G, because F is the connected pore, G is the connected pore, and this is what will be constituting the flow, right? It will allow us to recover fluids from it. So this is the main guy. This is the guy of importance. So effective porosity is F plus G upon bulk volume. Okay, effective porosity is of course it's lower than the total porosity, but it is the word of importance, and this is what we'll be using in our calculations later, right? And this is effective porosity. Now, for example, F is such that it has hydrocarbon stored. So this is what hydrocarbon porosity. Okay, now there is another way to measure hydrocarbon porosity, which is using the saturation. Okay, now I'll give you one more definition. So this is porosity, guys, right? This is porosity. I'll come back. I'll give you calculations related to porosity. But just because I want to define hydrocarbon porosity, I need to tell you what saturation is. Okay. Forget it all. Let's imagine पानी की टंकी. Okay, घर पे पानी की टंकी सबके होती है. तो उसमें आप ऐसे कभी बोलते हो कि पानी की टंकी आधा भरा हुआ है, आधी भरी हुई है. तो आप आधी भरी हुई से आपका क्या मतलब है? You imagine the entire water tank as a giant pore, okay, and that's your porosity. Now, inside that pore, half of the pore is full of water, okay. So what's happening is your water tank has 50% saturation of water, right? So the official definition of saturation is, So the official definition of saturation is, it is defined as the fraction of pore volume which is occupied by a particular fluid, right? So that makes us say that there can be a fraction of pore volume which is occupied by water, there can be a fraction occupied by gas, there can be a fraction occupied by oil, right? In your water tank example, half of the tank is occupied by what? Occupied by water, but the other half is occupied by gas or air, right? So saturation of water, which is 0.5, आधी टंकी भरी हुई है, so 0.5 is the saturation of water, plus आधा हवा से भरा हुआ है, तो saturation of air is also 0.5. The summation of both these saturations is giving what? 1. Exactly what is happening in the reservoir as well. So the saturation is, let me write this down. Saturation is volume occupied by fluid, let's say fluid F, divided by the pore volume. So this is saturation of F, right? So our oil and gas systems are oil, gas, water. These are the three guys important for us. So saturation of gas is volume of pores occupied by gas divided by volume of pores. Similarly, saturation of oil is volume of oil divided by volume of pores. Saturation of water is volume of water divided by volume of pores. And if you sum them all together, you can see that V gas plus V oil plus V water, and that's what is contained inside a pore, right? If this is a pore and this is gas, oil, water, the summation of all those constitutes the pore volume, right? That is why we say that the summation of saturations gives you 1. right? So coming back to hydrocarbon saturation, what is hydrocarbon saturation? Hydrocarbon saturation is the overall porosity, not saturation, hydrocarbon porosity. Hydrocarbon porosity is the overall porosity, the effective porosity multiplied by saturation of hydrocarbons. This is important. Some people write it as 1 minus SW. You can see that hydrocarbons, right? So Sg and SO, they can be together called as SHC, which is gas and oil are both hydrocarbons. So 1 minus SW, because all of these are 1, so 1 minus SW gives you SHC. So it is 5 multiplied by 1 minus SW as well, right? So this is hydrocarbon porosity. Now we'll talk about how to measure porosity, okay? We'll talk about, okay, if you want to, write it in a different way, porosity is the bulk volume minus grain volume divided by the bulk volume. How's this for a definition? Great, right? Because this is what? This is, overall this is pore volume, because this is your rock and it has some grains and some voids. So if you take the bulk volume, subtract the grains of it, you'll be left with the voids. And that is what is considered in porosity. Porosity is pore volume by bulk volume. Okay. So this is it for porosity. You need to measure either of these. You can measure bulk volume using the vernier calipers, and you can measure the scales. And if it's a cube, you can measure LBH, and if it's a sphere, you can measure 4/3 pi r cube and things like these, and that give you the bulk volume. Now you can measure the grain volume by crushing the rock. That will give you the total porosity, because what's not crushed is the void, right? So if you have this, for example, this is your rock bulk. Now if you crush it, you can see that there are a lot of spaces in it. So rock bulk is comprised of solid part as well as the voidy part, the empty part. So if you crush it, what will happen is it will give you the grain volume, because the crushed part will be the solid part, right? So this is the grain volume, and this bulk volume minus the initial bulk volume minus the grain volume will give you the pore volume, and if you divide it by the bulk volume, you get the porosity, right? So now we'll move further. I'll delete a bit of space. Now we'll talk about how to measure porosity and what are the various sources available in oil and gas industry, E&P cycle that give you porosity. Different sources are there. आप लॉगिंग पढ़ लेना, उसमें भी आपको पोरोसिटी कैसे नापना बताएंगे, तो वही मैं बताने वाला हूँ कि कहाँ पे एक्सपेक्ट कर सकते हो कि भाई साहब पोरोसिटी आने वाला है, ठीक है। और एक और बात कहना चाहता हूँ, मैं कभी कभी धीरे बोलने की कोशिश करता हूँ, बिकॉज वी नॉट परफेक्ट एंड और ये वॉइस एको होता है और सब होता है, तो लॉट ऑफ पीपल हैव इट difficult to understand things. So you can watch my videos. I always watch YouTube videos on 1.5x or 2x. You can go and watch it 1.5x. Okay. And if there are any suggestions you want to give me about my speech or something, please do, because it's my first time, of course. Right. So yeah, ways to measure. Porosity. Right? So there are direct ways and there are indirect ways. Right? What's the direct way? There is a Boyle's law principle. I'll cover that later. Not in today's agenda. There is a rock crushing. There is a fluid saturation. Fluid saturating. They also call it leaching method, right? So these are the things that come to my mind. Boyle's law is nothing but it's like hota kya isme? You have two chambers which are connected to each other, but initially there is a wall which is disconnecting them. The volume is V1. This chamber's volume is V2. एक के अंदर you are storing your rock sample and the other is empty, right? So not empty, but a particular gas is filled. Now what will happen is both have their initial pressures P1 and P2. Now you open the valve in between and the pressure tries to equalize, because it's the rule, physical rule, because एक side pressure दूसरी side pressure उसको connect कर दिया तो दोनों का stabilize, एक uniform pressure आ जाएगा. Final volume. So Boyle's law, it's nothing but PV equals to constant. For those who are enthusiastic enough to think about it, you can think about it. I'll come back to it in later classes, right? When we'll have a detailed description about how to measure. It's not that important. Boyle's law is important, so I'll come back to this later. Okay? But I have to cover other things. So indirect parameters, they involve logging. Which log gives you porosity? That can be a common question. Neutron logs, density logs, sonic logs. How they give you porosity? Density log तो सबसे आसान है भाई. आप खुद सोच सकते हो कि अगर एक चीज बहुत डेंस है तो उसका porosity कम होगा, एक चीज बहुत ज्यादा porous है तो उसका density कम होगा. So एक तरह से density is inversely proportional to porosity. तो उस फिनोमेना से आप डेंसिटी लॉग से पोरोसिटी निकाल सकते हो. सोनिक लॉग है तो वही बात है कि अभी जैसे सॉलिड है तो इधर मैं अगर बोलूंगा तो इधर तक जल्दी पहुंच जाएगा. बट इफ आई रिप्लेस दिस विद open space or a void, the time taken by sound to travel from one point to the other will take a longer time. So that is how you measure the sonic based on the transit time. Right? If you ask him about the equation, it's a very common equation, right? The Wiley's time average equation. Nothing. It's absolutely nothing, and you will score a lot of marks from this. Like overall, जो time मिल रहा है आपको, overall जो चीज मिल रही है, for example, the transit time. It's a combination of जो porosity की वजह से time lag हुआ, plus जो मैट्रिक्स या फिर सॉलिड पार्ट की वजह से टाइम लैग हुआ. दैट फ्रैक्शन इज गिवन बाय 1 minus 5 and the fraction of porosity is given by 5. So if it's density, you can say rho bulk is rho fluid into 5 plus rho matrix into 1 minus 5. If you solve this, this is known, this is known, this is known. If you solve it, you get the porosity. This is how logs give you porosity, right? And that's not in the agenda, but yeah. This is a lot about porosity. Now we'll move forward and cover other things. Okay, one important thing is, if you crush a rock, and what will happen is, for example, this is your rock, and then you crush it. You crush it with a hathoda, right? And then you crush it by mortar or pestle or something, and it turns out to be a crushed form of grains, right? These are the grains. Now, if you remember, I gave you this definition of porosity. Now, this volume is known, the grain volume, you know this, right? So this you know, this you had initially known, LBH. So this you know, so you can find porosity, right? But the actual part, the important part in this definition is what you get is total porosity. But if you're talking about this gives you total porosity. But if you're talking about this method, this gives you effective porosity. Because this method, what happens in this method is, you calculate the dry weight of the sample. You have a rock sample. Okay, when I'm saying sample, I'm talking about a core sample, okay? So you have a dry core, then you saturate it or you wet it with a particular fluid. The weight of that core increases, right? So the differences between both these weights, it will try to give you the porosity. We'll try to cover numericals. बहुत सारे numericals हैं इससे related, but just to give you a base. Now, why it gives you effective porosity? It's because जो भी fluid saturation हो रहा है, it will happen in the connected pores, right? It will happen. Fluid is going inside. It's increasing the weight. It cannot go inside the isolated pores, right? So that is why this phenomena gives you the effective porosity. The crushing phenomena, it gives you the total porosity, right? And coming to logs, the sonic log helps you give you the secondary porosity. Just a benchmark, if you can remember right now, the logging guys will cover this, and the other logs give you the total porosity, right? So this is all about porosity. let's move forward. Yeah. When I was a kid, I always used to dream about getting the task to clear the boards and all. I used to love it. Never knew I would get to do it someday. Thanks, guys, for giving me this opportunity. Alright. Now, I'm going to talk about something that you might have never heard of, or you might have. It's called isothermal compressibility. Rock, because it's a rock. It's isothermal compressibility. As always, going from scratch, this term, it gives you the brief idea itself. Compressibility. Okay. If this is a rock sample and I'm trying to compress it, it will try to change the volume. Maybe it has. So there's a change in volume. There was an initial volume with respect to whose you're calculating the volume change, and there is a pressure that you applied. So these three things constitute what we call as compressibility, right? Because over the years, the rock sample has converted from this huge to this much, because it's deep inside the earth. A huge dinosaur is now not even this much, because it's compressed over the years. It's crushed and it's pressurized, and it's gone through a lot of volume changes, right? Due to what we call as overburden, right? Not just overburden, but a lot of directions of pressure are coming to it. So this is what we are talking about, right? So the official definition of compressibility is -1 by V del V upon del V. And not to forget, at a constant temperature. Why constant temperature? Because we are assuming that whatever pressure is applied to this particular sample, it's all taking place, it's all been occupied in converting the volume change, right? मतलब इजी भाषा में बोले तो जो भी मैं एनर्जी दे रहा हूँ वो पूरा की पूरा एनर्जी यू आर यूजिंग टू चेंज द वॉल्यूम. देयर इज नो हीट change in the system. If anyone understands thermodynamics, the entire energy is used to convert the volume of the sample. So that is how ideally you describe the isothermal compressibility. Okay. बहुत important चीज है. If you'll be talking about well test analysis, you will be understanding why it is important. It's very important because these are the things that give you the response of a formation pressure with respect to time and space and all. We'll cover that. Okay. So compressibility is, for example, this is my sample. Its initial volume is 10 units, let's say, and it changes to a small sample due to application of delta P pressure, which is 100 units. We're not talking about unit dimensions right now, just to understand the concept. It converts to 1 unit, let's say centimeter cube or something like that, centimeter cube, right? So what's the compressibility? Compressibility is 1 by initial volume. This is the initial volume, which is 10, multiplied by, now minus sign is there because otherwise you can see that with the application of pressure, increase of pressure, the volume is decreasing. So this overall term will be negative. But compressibility is a property and we cannot have it negative. So multiplied by negative. ये सब चीज बोलने के लिए बोलते हैं, लेकिन overall हमको करना क्या है? हमको ये करना है कि we have to measure it in a way that entirely we get it as positive. So I'm explaining that over here. So this is the volume change. The delta V is 10 minus 9, 10 minus 1. So it's 9. Basically, del V is supposed to be V final minus V initial, but then we multiplied by -1. So it's basically a setting which is converting everything to a positive number. So that's what I'm doing. So this is 9 and divided by 100 because this is the pressure. So you can say 9 into 10 to the power -3 units of 1 by pressure. right? So this is how you measure compressibility. Mean calculate permeability. There are ways to measure compressibility. I'm sorry. Right? Now, in a rock, you have two things. You have a grain, the solidy part of the rock, and you have the fluidy part of the rock, or the void part of the rock. So both of these things have their own compressibilities. So the overall compressibility of the formation or the rock sample is a composite of both of these things. A composite of the rock compressibility and a composite of the pore compressibility, right? So these are the two things. Because the pore will be porosity, right? It will be given by porosity. So this is the rock and this is the rocky part of it. And this is the porous part of it. So this will have some porosity, this will have some porosity. So if you are trying to crush it, this will crush just a bit, but this will crush a lot. So this normally dominates and this is normally neglected. But in terms of unconsolidated rocks, like if you go to a garden and you see a wet lump of sand, you can call it unconsolidated rock, because if you try to put your hand on it, it changes. The sand also tries to lump together. So the rocky part also is compressible in that case. So this is shallow rocks. Okay, in these kind of rocks, this cannot be ignored. So this is total compressibility. Now I'll try to explain you what's effective compressibility. I mean, it's a very popular question. Gate में भी आ सकता है ये सी. Effective compressibility. Okay. Just a second. Yeah, so we're talking about effective compressibility, okay? So effective compressibility, let's say we start with the bulk volume. What's the bulk volume? Should I clear some space for you guys? Okay, I'll clear some space. Alright. So this is bulk volume. It's V rock plus V. Let's say if it's just containing oil, okay, so we'll say V rock plus V oil. Okay, now this equation will differentiate it with respect to pressure. Okay, del Vp by del P or dVp by dP by del P plus del VO by del P. Right? And now we give it the equation number 1. Okay, now by individual definitions, if we are talking about bulk compressibility is what we are calling the effective compressibility, and it will be given by 1 by V del Vp by del P, right? And this is what Vp. So this guy is what? Minus Ce times of Vb. Okay, remember this. This guy is minus Vb times of Ce. Okay, this is one thing. The second thing is, if you're talking about rock compressibility, it is equals to minus 1 by V grain or V rock and d del of V rock by del P, right? So, or you can say V rock. Okay. So this guy is what? Minus Cr times of Vr. Right? And this thing, CO, is minus 1 by VO del VO by del P. And this guy is what? Minus CO VO. Okay? And these three things will substitute in this. Okay? So what we get is minus CE VB equals minus CR VR minus CO VO. Simple. So this turns out to be positive. This is our second equation. Now, in this, if we take this and divide this with the entire equation, the CE is CR VR by VB plus CO VO by VB. What is this thing? Yes, it's porosity. What is this thing? What is VR? VR is VB minus VO. So VR by VB is VB minus VO divided by VB. So it's basically 1 minus 5, right? Think about it. So CE is CR 1 minus 5 plus CO 5. And that is the definition of effective compressibility. Isn't it nice? So these are the few things that we talked about, okay? And I have some more things to share with you. Sorry for the noises. Okay. As we go along and make more videos, maybe we'll get more experts in this thing. But right now, just focus on the content. Okay? So yeah, what I was trying to tell you is, suppose this is a rock, which is like, this is the sea level, and this rock is huge depth below the sea level. Now, this is the pole. This is the pole, right? This is the pole. Let me color it in red so that you don't get confused. This is the pole. अब हो क्या रहा है? बाहर से प्रेशर आ रहा है, P external, overburden, P external, और अंदर से भी प्रेशर आ रहा है, internal, because fluid है, बाहर से तो external pressure लग ही रहा है, but internal fluid pressure भी तो है. So these absolute values of pressure are not important. What's important is the P net, which is P external minus P internal. This is important. Important where? In the definition, you can see that 1 by V del V by del P, right? So in pressure, this is important because this is the part which we'll be using in it. The P net is important, okay? The absolute values are not important, right? Okay, so this is just something that I wanted to convey. Over the years, if P net is varying and P net is varying, we have to focus on P net rather than P external or P internal individually, right? So this is one thing. Other thing is limestones and sandstones. If someone asks you, limestone and sandstone, their compressibilities are of the order 10 to the power minus 6 psi inverse. This is the field unit of compressibility. It can be 2, 3, 5 or whatever, 2 to 6 or whatever. But this is the order that you have to remember, right? So you can see how low. It's very low, right? So unconsolidated rocks will have higher compressibility. They may be of the order 10 to the power minus 4. But normally compacted rocks have this levels of compressibility. How do you measure compressibility? There are triaxial cells in the laboratory. What they do is they have a rock sample and they try to apply stress from every direction and they try to compress the rock as compared to its initial position. And then they try to measure the compressibility just like the way I told you. So why triaxial, why all these directions are being considered is because in Earth, for example, you are standing above the ground. So below you, if you are building the house, you lay brick by brick by brick. So a brick in the center is crushed along by bricks on each side, right? So your pressure is not just one directional; it's being applied from each and every direction. So that is why you have to consider a triaxial cell. People only talk about overburden and all those things, but in actuality, pressure is being applied from the top, from the bottom, from all directions. That is why to get the real picture of the formation stresses, you have to use the triaxial cells, right? So, moving forward, next part we are talking about formally is fluid saturations. We've discussed a lot about it, but I'll just try to cover what we have not covered. A few important terminologies about saturation. Yeah. So what we have covered about saturation is it's the volume of fluid divided by the volume of pore. That's one thing we have covered. Okay, so there's a bulk volume. A portion of that bulk volume is porosity. A portion of that porosity is saturation. You see how we are going? We're going from bulk volume, and then we reduce the green part of it, we get the pore volume, which gives you the porosity. Based on that pore volume, the volume of fluids give you the saturation, right? Every sort of volume that you can imagine in a rock will give you a particular parameter of the rock property. So this is how we go about things. So this is one thing, and the other thing we have considered is SO plus SW plus SG is equals to 1. This plus this is SHC. So SHC is 1 minus SW. Alright. So this is something, and we'll cover a few more things. How we measure saturation. Measurement of saturation. So what's happening is, this is our earth. Okay, this is our well that we are drilling. We are drilling, right? This is our bit, this is our surface, this is our POP, just to get you a feel. This is our rig, right? So what happens is, there are different kind of bits called the coring bits. What they do is they recover rock samples from the bottom or from the zones of interest. Then they carry it up to the surface. Here's a laboratory, right? Here's a laboratory. You have to preserve the core sample and take it to a laboratory where we do two kinds of tests. One is the routine core analysis tests. One is the spatial core analysis tests, right? There are different properties that we measure in both of these tests. In routine core analysis, we measure the porosity, the absolute permeability, the saturation, right? And in scal properties, we measure our capillary pressure, wettability, relative permeability, etc. Right? So these things are basically deciding how fluid flow will be taking place. They basically decide how interactions are taking place, how rock is behaving along with fluids and all. These are the detailed part. The next section will be covering about scal properties. Right now we're talking about routine core analysis properties. Okay? So, measurement of saturation. Once you have this core sample in your laboratory, what you have to do is you have to measure the saturation, right? And the properties, the measurement methods are, one is, I'll just clear this. There are direct methods and there are indirect methods, as always. So, there are direct methods. There are indirect methods. Indirect methods, there is popular method called retort method. In this, what we do is you have a rock sample and you heat it. You try to eject all the fluids out of it, and then you get the saturation, right? And in indirect, again, you use the logging techniques, in which the popular Archie's equation is used in the resistivity law, right? So this is how you measure saturation. Okay. Now we have an interesting task in our hands. We have discussed about porosity, we have discussed about saturation. Now we'll talk about why do we need to understand porosity and all these jargons. What is the task we are aiming to achieve from this? That is what I'll tell you. We'll solve a numerical. Okay. So we'll try to call this numerical an application of effective porosity in calculating N. What is N? N is original oil in place. Okay, we're talking about the reserves. I want to talk about one thing here is Will you consider the total porosity while calculating the reserve, or will you consider the effective porosity if you are talking about a reserve? Now you'll ask me, what is a reserve and what is a resource, right? The entire accumulation which is inside the subsurface, it can be called in two ways. One is reserve and one is resource. A resource is something which is there, it's totally there, but just a part of it can be recovered, and that part of it which is recoverable from the given date forward is called a reserve. So that is the information that we need about reserves, and the reserve is called the original oiling place that can be recovered, OOIP, original oiling place, and we have to consider effective porosity to calculate the original oiling place. Courtesy Tariq Ahmed, right? So I'll give you a few parameters and you can try to solve it if you can. Okay. Here I'll try to derive it, and here I'll try to solve this question. But the data that I need in this question is the cross-sectional area of the reservoir is. The cross-sectional area of the reservoir is 640 acres. The thickness of the reservoir is 10 feet. The connate water saturation of the reservoir is 0.25 or 25%. The formation oil volume factor, which is just a conversion factor that takes the oil from the bottom hole or the reservoir conditions to the surface units, it's 1.396 reservoir barrels upon stock tank barrels. The effective porosity that we have calculated by one of these methods is 0.15. You never use the percentage version of the porosity in your calculations. You always use the fraction version of your porosity in calculations, right? So what we have to find is, we have to find N. Okay? If I try to draw a diagram of it, this is our reservoir rock. Okay? And this is the area. This is the thickness. No, this is not the area, this is the area. Okay? This is not clear, but yeah. Area. Yeah, this is the area. Wow. You see, I'm trying to solve with you guys. So this is the area and this is the thickness, and which will give you the bulk volume of the reservoir. Okay, so bulk volume of the reservoir is area into thickness, but since area is given in what? Acres, and thickness is given in what? Feet. The bulk volume that we have received is in acre feet. Note that 1 acre feet is equals to 43560 feet cube. Right, so we substitute this over here. So the bulk volume is AH into 43560 feet cube. This is our first equation. Now, we know that porosity is pore volume upon bulk volume. So the pore volume is porosity times of bulk volume, right? So the pore volume over here is porosity times of AH 43560. Right? Now, this is second equation. Now, in this pore, if you multiply this by saturation, you'll get the oil volume, right? Ultimately, that's what our target is. The volume, what's saturation? Saturation is volume of oil divided by the volume of pores. This is the pore volume. You can get the volume of oil by multiplying it right here. So, the oil volume is SO into VP, right? What's SO, guys? SO is 1 minus SWC, 75%. So 1 minus SWC into VP, it gives you the VO, right? So we get the VO over here, and now we try to expand it. VO is 1 minus SWC into VP. What is VP? 5E AH into 43560. The unit is feet cube. And the answer we need is in STB. N is always calculated in surface conditions, that is stock tank barrels. So this is VO and it's in feet cube. Remember, one barrel is 5.615 feet cube. Always remember, this is bread and butter. This is oxygen for oil and gas. This unit conversion is very important. Okay. So one barrel is 5.615 feet cube, and 1 feet cube is 1 by 5.615 barrels. So you try to substitute this feet cube by 1 by 5.615. So VO becomes AH5E 1 minus SWC multiplied by 43560 upon what? 5.615 barrels. Now BO, the unit of BO is some value RV upon STB or barrels upon STB. So if you divide this whole thing by BO, will we get N or not? Yes, we will, because BO is in barrels upon STB. So this barrel and barrel will get cancelled out. STB will go up. So the final formula for N is 43560 by 5.615. What is this? I remember this, but you can calculate it and you can find it 7758. AH 5E 1 minus SWC by BO STB. This is what the question is asking us. It's a typical gate level question, guys. Always remember. It can always come 2 marks, numerical answer type. So yeah, so now we'll do the simplest part of our question. We'll substitute values 7758 into area, which is 640 acres, into height, which is 10 feet, into 5E, which is 0.15, into 1 minus SWC, which is 0.75, divided by BO, which is 1.396. What's the answer? The answer is 4,400, let me write this, 4001153, something like that. Don't worry, because if I've calculated it from scratch, right? I've calculated this ratio rather than just standard 7758. So there can be a slide because this is a huge calculation. But if your answer starts from 4 and its the number of digits are, it's up to here, okay? Its number of digits are same, you can go and have your drink. So this is fine. So this is one numerical that we can solve. Now I'll talk about something very important about saturations, a few terminologies. I hope you have understood this question, and I'm trying to rub it. Yeah. So this is a theoretical lecture. Don't worry if you think not covered questions. I covered questions in subsequent lectures. But this is a good practice that we did right now. Don't get confused. If you get confused, you can ask me. Saturations. Types, or it's not fair to call them types, but different kind of saturations, or the terms related to saturation that you will come across. One is cooled water saturation. One is critical saturation. It can be for oil, water, gas, any phase. And one is residual saturation. Okay, yeah. So let's talk about these guys. So connate water saturation, the word connate means by birth. Okay, जब रॉक जमा हो रहा था उसके अंदर ग्रेन्स एक के ऊपर एक ऐसे ऐसे करके जमा हो रहे थे, तो उसके अंदर जब बीच में कुछ फ्लूइड्स, बारिश आ गई होगी या कुछ पानी कहीं से रिवर्स या कहीं से आ गया होगा, तो सम फ्लूइड got collected while grains were trying to form a rock. So the rock was having its birth at that moment. The rock was trying to get converted from sediments to a rock, and some fluid came along and it said, okay, I'll be a part of you as well. That is called connate water saturation. It's in the smallest of pores, and it's by birth, it's the part of the rock, something like that. So that's connate water saturation. Now this is important, critical saturation. I'll try to give you a perspective. For example, you have oil in the reservoir. Oil can have gases dissolved in it, but that requires a higher pressure because gases are dissolved. So let's say the reservoir pressure is higher than bubble point pressure initially, and gases are dissolved in oil. So over the years, the pressure is trying to deplete. So the pressure goes below bubble point. Gases try to come out of the oil. Now gases try to flow, but they cannot flow because they are disconnected and they are scattered. Their saturation is very low. Why gases cannot flow is because their saturation is less than something called as critical saturation. They lack continuity, or they lack a saturation good enough for them to develop a streamline or to develop a flow. So this is called critical saturation. A saturation which, if it gets higher than critical saturation, then you can say that the phase will flow. Otherwise it won't. So the critical saturation is a saturation which is a must for a fluid to flow. Okay, if oil is at a saturation lesser than critical saturation, oil will not flow. If oil is at a saturation higher than critical saturation, oil is flowing nicely. Similarly for gas, similarly for water. Okay. However, you can see that this is trying to talk about the case where flow is trying to start, right? So this is important. This perspective is important. This critical saturation is at the start. If you're trying to make oil flow, that is when we will be talking about critical saturation. If you're trying to initiate flow of a phase, we'll be talking about critical saturation, which differentiates it from residual saturation. Residual saturation is the case when the fluid cannot flow anymore at the end, when the fluid becomes immobile. So residual saturation is when we talk about things like EOR and all. It's not particularly, most people like to call it the remaining oil saturation, that's other nuance, but right now residual saturation is something at which also the oil or any particular phase, it becomes discontinuous again and it cannot flow anymore. At the end we are talking about. This is at the start and this is at the end. Okay, so I hope you now get a clear picture about how saturations are. Okay. Now there's one more thing. It's called the movable oil saturation. So movable oil saturation is 1 minus SWC minus SOC. Right? If you're talking about the initial state of a rock, okay, the initial state of a rock will have SWC and SOC, which cannot flow. So SOM is basically 1 minus SWC plus SOC. Right? So this is called the movable oil saturation, and these are the few kinds of saturations. Right? Now we'll talk about porosity averaging and saturation averaging, and that is important if you're talking about a heterogeneous reservoir, because a reservoir is huge. You cannot say porosity here is equals to porosity here, or porosity here is equals to here. it is varied, right? There are different kinds of environments in one city. If you go from Rajasthan to Jammu Kashmir, the areas are different. If you go from one part of a reservoir to the other part of the reservoir, the conditions are different. Porosities will be different, saturations will be different. So you need to find a way to calculate statistical ways to calculate average value which can sufficiently conclude for a representative reservoir, right? You can say that this is representative for the reservoir. You can say that this is a good average for the reservoir. So there are a few ways by which we measure the porosity averages and saturation averages. So it's very easy. So I'll just write it down for you. Porosity averaging and saturation averaging. Okay. So porosity average, the first method is arithmetic average. So phi average arithmetic is equals to phi 1 plus phi 2 plus so on up to phi n upon n. So what we are doing is we are calculating porosity at first point, second point, third point, fourth point, bringing it all together, divided by the number of points, you get the arithmetic average. Okay. Second is thickness weighted average. For example, this is your rock. There are 3 layers, 1, 2, 3. First layer has h equals to 10 feet. The second layer has h equals to 20 feet. Third layer again has h equals to 10 feet. The first layer has a porosity of 0.2, second has 0.5, third has 0.1. Right? So the average porosity of this is phi 1 H1 plus phi 2 H2 plus so on up to H1 plus H2 plus so on. Right? So in this case 0.2 multiplied by 10 plus 0.5 multiplied by 20 plus 0.1 multiplied by 10 divided by 10 plus 20 plus 10. This is thickness average porosity. Third is areal average, areal weighted average. You have the picture by now. Phi 1 A1 plus phi 2 A2 plus so on up to summation of A, various A1 plus A2 and all. This is important, guys, when you are talking about the areal extent and you're talking about the various, for example, this is the part of the reservoir which has a different deposition environment. This area has a different deposition environment. So the conditions are varying from one place to other. So you consider the areal weighted average. Now the maximum averaging that we do is like in volumetric average, which is phi 1 V1 plus phi 2 V2 plus so on up to summation of V1 plus V2 plus, right? So this is the summation. So this is volumetric average. Very easy to understand, self-explanatory, and there is a common technique for saturation averaging, which is summation of phi I hi si upon summation of phi I hi. So the questions you will get will look like this. For example, this is the H table, this is the phi table, this is the serial number 1, 2, 3, 4, and you have to develop the overall saturation average for this thing, right? And the corresponding saturation for each serial number, right? So you find out the phi HS for each serial number. For each serial number, say you get this one is 0.2, this one is 0.4, this one is 0.6 by multiplying these 3 guys. So you get the total. The summation means the total. So in this case, this is the total you get, right? And phi into h, where is phi into h? This is, you say this is T and this is T. So the ratio of these things gives you the average saturation, right? All right. So covered a lot of things today, and this is the last part of today's presentation. The books I'm referring right now, they are Tariq Ahmed and Kraft Hawkins, BC Kraft and Hawkins, And these are the things that you can easily find there. If you want to practice things, you can go and practice on the books. I'll come up and talk about questions later on, later parts of the presentation. Okay, then over to you guys. Best of luck. Do well, prepare well, right? We'll see you soon. Bye-bye.